Yeah, this is much familiar now, I guess.
Do it.
All right, so starting with, all right, so in 11 you compared your displacement with the volume of each slice. Now, you can argue which one of those would be more accurate. The displacement would be reasonably accurate, although, you know, your marks are only every 50 centimeters, right, on there. So, is that right? The markings on there. So, you know, you are estimating that a little bit. The so that could be off. The slices, depending on how well you cut them, you know, but that could be off just a little bit there. But anyway, we're reasonably close, about like we are most of the times when we do this. But the idea is the volume limit. Now, either one of these methods, though, has extreme limitations. We talked about if we were engineers designing some, you know, big piece of machinery or some part, you know, for example, we were designing some part for some sort of thing that looked like this, and we wanted to know the volume of this. Both of these would have limitations. Number one, the part might be so big that volume by displacement and then slicing it up might not be a great option anyway. And not only that, but our slices were not that accurate because remember, we were just doing like an average radius and those kind of things. And then the other limitation would be this might not even be a real thing. Of course, with 3D printers and stuff now, you know, you can actually design something, print it out real quick and whatever, have a small model. But so the idea is if it's not even a real thing, real object, then the idea of, you know, being able to do displacement or actual slice of the physical thing is not, you can't do that. So what would be a mathematical way to calculate this? So what we're going to do, and you probably already can see where we're going with it, depending how far you got, is we're going to say, let's take this method of slicing and the volumes and let's add up the slices, right? And of course, what do we have in calculus? It's an adder. The sigma, which turned into the integral, right? The integral is adding up these pieces. Now, if we take the integral that we know right now, you don't have to write this down, but when we first learned about the integral, it was area. And then when we got into the section with the sigmas, we realized that this is really the height of a rectangle and this is the width of a rectangle. And so height times width gave us area. So this particular thing gave us area of a region, area under a curve. And then, of course, we got into these kind of problems where we had this, and we realized that this was miles per hour, and this was hours, and so then this gave us miles, and so all of a sudden we found that we could do position or distance, and really there's an adding component here, because what we're doing is kind of rate times time. We're kind of saying, okay, if I'm changing my speed all the way along, I can add up tiny little segments of that, where if I take tiny little units of time, my speed didn't change that much. And so what I can find is how far I traveled there. So my rate is almost constant, right? And I take little tiny pieces of it. Just like when we do a left rectangle, it assumes the graph stays constant. But if we take real tiny rectangles, right, the curve almost does stay constant. It doesn't move very much in a small amount of time. So what the integral down there is doing is adding up little bits of miles and giving us our total miles when we add it up. All right, so we're taking that same concept and applying it here. So this red thing is one slice of the lemon. The volume of that slice is that. So you guys did 6 slices. Okay, the key thing I want you to notice is this piece right here. This strip. This strip is the radius of that red slice. Now, every time we do a slice, that radius changes, correct? So that's where we got this function to stand for the radius, okay, because it's a changing amount. So this function value is the radius. So when you wrote your sigma, so let's back up. So in number 12, it said, in your pi r squared h, what is the calculus name for the width? What did you put at the top of, it was number 12, actually went around to the top of the next page. Delta x would be a good answer for that right there, because the width of our slice right here, the width is that delta x. As we do more and more slices, that gets narrower and narrower and narrower. Then in 13 it said, what was the expression for the radius? What were they looking for there? Hint, hint, it's that function that we found when we did the quartic regression. It's the f of x, and you didn't have to write it all out again. If you did, fine. If you didn't, if you just said C problem 5, whatever. But what they were doing there, what they were saying is that this function here is the radius. I want you to really picture this red slice here. This function, this strip, which is the y value of the function, that strip is the radius of each of the slices if we drew a bunch of slices in here. Okay, well now if we want to add those up, so then they said, okay, if you're going to add up 10 slices, 100 slices, what would be the sigma for that? Now I did it with 6. Now here's what I wrote. Now yours might look a little different than this. Maybe you wrote f of x in there. But isn't this the pi r squared h right here? And you didn't all get that far. I get that. But do you see what we're talking about? We want the sigma to add up the volume of the 6 slices. Well, the volume was pi r squared h. Now I know we averaged the radius and so forth, okay, but we're gonna just say right now that we have one output value, and that's our radius. Because as we did thinner and thinner slices, right? Does that make sense? If we did 100 slices, this side and this side would be pretty much the same thing, right? So the averaging part wouldn't be that big a deal, okay? So what we're adding up is pi r squared h. The h is the delta x, the f is here. Here's how you get the I in there. If you remember when we did that with Riemann sums, we called that f of c sub I, so that's f of c1, f of c2, f of c3. That was your sampling points along the way. Now, if you change this to 10, or you change this to 100, now, you might have been even pickier. Maybe instead of a delta x here, you guys wrote 8.2 divided by 6, whatever that was. And 8.2 divided by 10, and 8.2 divided by 100, and then if you go from 1 to n, maybe that would have been 8.2 divided by n. I mean, if you did that, that's good. That's good thinking, because that's how specific it would be for yours. But if you just put delta x, I'm okay with that. Okay, and yeah, we could have got even pickier in here, right? We could have done, on this one, let's say mine was 1.5. So would that be 1.5i? Right? I equals 1, it'd be a 1.5, I equals 2, it'd be a 3. Right? I mean, I could have had that on the inside of there if I really want to get picky with the sigma. But I want you to just see this. It's pi f of x squared delta x. That's what I care about. Now, so as n goes to infinity, so then they ask you about the infinite then. In problem, what are we in now? About number 14, 15 there? They talk about the infinite number, right? And so we get this. Well, we know an infinite number of things being added turns into an integral. And so look what we got. We got pi f of x squared, and the delta x turns into just our dx. Okay, now I want you to notice something about, so now, what you're supposed to do is go onto your calculator screen. Has anybody done this yet? This is number 17 now. 16, you write that integral. Now, some of yours would go from 0 to 8.2. Some of you would go from 0 to 8.8, or whatever your integral was. Now, the f of x we've already got defined, correct? Didn't you already define that in your calculator screen? Should have. And if somebody in your group has, if you didn't, then somebody in your group certainly has. So we can type it in just like that. So for number 17, what you're supposed to do is you're supposed to type in your integral that you write in 16, be the integral from 0 to whatever your end was. Mine would be 0 to 9 up there, and then pi f of x squared dx, and that should give you an answer that you could compare to your displacement and your slicing answer. Now we'll see how good these middle group did. So is very close. Now, to be honest, this should be the least accurate anyway. Okay, you guys were around 195. What'd you get?
102.
102, yeah. There are a lot of problems with the integral way of doing it, and they say, well, why, geez, that's the calculus way. No. Well, think about where this f of x came from. It came from your sketch of your pencil around the lemon, which is pretty tough to do. And then you measured those values, and then we fit a curve to that, called it f of x, and then we put it into this integral. There's a lot of places there for that to go off. So normally, our answer there is not that great. Anybody get closer? What did you guys have? And your slices were 2 something? 200 or something like that, right? Yeah, so you're right in the ballpark. So that's pretty good. So your integral is 180 something, your displacement was 170 something, okay? Yeah, but, okay? But here's the really, hey guys, now here's the really new thing on this. What we're used to seeing is we're used to seeing just integral of a function dx, right? Integral of f of x dx, or maybe it's f prime dx, whatever. But we're not used to a formula being, well, I guess I take it back, arc length. Remember arc length? Square root of 1 plus f prime squared. That was a formula, and that came from Pythagorean theorem. I forgot about that. What we were doing there is we took our integral, we did our Pythagorean theorem, which gave us a formula for one piece of a little bit of length along a curve, and then we had the integral add up all those little lengths. So this would be connected to that. Okay? So now I want you to notice something with this. All right? Now here's what we're going to take forward from this. Right here, that right there came from pi r squared, which is the shape of this slice. This slice is a circle. Now I heard people saying circle, and really it was a cylinder, right? Because it's three-dimensional slice. But think about it. If you did 1,000,000 slices, what would each of those slices look like? They'd be paper thin, right? I mean, if we could put it in one of those deli meat slicers, right? Take our lemon and put it in one of those things, right? We could slice those, we could have these lemon slices just be paper thin, where the width would be almost nothing, and that's what we're talking about. So if you looked at one of those, it would be like a piece of paper. It's like this. If I hold this up and you say, is that two-dimensional or three-dimensional? It's three-dimensional, but that third dimension is really, really narrow, right? We normally think this is two-dimensional, right? But it technically is three-dimensional, because if you take 1,000,000 of these and stack them, you're going to have that third dimension, and that's what we're talking about. Okay? So, the dx is kind of that third dimension on this. So this is area, and this is that. Now, so that what that gives us is, let's see. Okay, don't write this down yet. Don't write this down yet. But just a quick little bit of geometry. So here I've got 2 different slices, for example. Now, the ones we're going to focus on for a few days are going to be circular slices. Okay, so all of the objects we're going to have are going to be these revolved, rotated kinds of objects that are going to, when you slice them, they're going to make circles, circular slices. But you can imagine, and I'm going to show you some objects that if we sliced them, they would make square type slices, or maybe triangle shaped slices. Well, all we would have to do to get the volume is go back to geometry, and geometry said the volume of one of these things is the base area, which I've shaded, times the height. Now the height is going to be the delta x part. That's going to be this thickness. Now remember, these are tipped up on end, so when I say height, it's actually this I'm talking about. That's the h. And then this is the area of the slice. Okay? So in general, our volume is going to be the area of the slice, whatever that shape is, times the delta x. So here's what I would have you write in your notes. Okay? So this is the formula we want to take forward. So to find the volume of a solid by the slicing method, we're going to imagine that this solid, and this only works when all the slices are the same shape. So if I have something that I could slice, if all the slices are circles, like these 2 things I have here in my hand, right? If I take these solids here, and I just started slicing, every slice would be a circular shape. Same thing here, but they'd be different sizes, right? They'd be different shaped slices, just like with the lemon. Okay, so those kinds of solids are going to have circular slices. Now we'll get into some other kinds of solids that have square slices and other types of slices. But for right now, in today's homework, there's like 5 problems, and they're all circle slices. But in general, the formula is going to be the area of the slice times then the dx is going to be the width of the slice. And that's what gives us volume, area times the width. area times width. It'd be like centimeters squared times centimeters, you get centimeters cubed. Okay, so it's going to seem kind of strange that we're doing area in our integral, but the answer comes out volume. But it shouldn't be that strange. We do f prime like miles per hour in our integral, and the answer comes out distance, right? So it's kind of the same thing. All right, so for us right now then, our formula is always going to be, for the problems we do, our functions are all going to be pi, I'm going to call it r of x squared dx. So the problems we're doing right now, ours are all going to be that. Okay, I'm going to call that r of x instead of f of x because, like we said, f of x was our radius. Let's just call it that. Let's call it r of x. It's a changing radius, that's why it's an r of x, not just a constant r. Okay? All right, so what's a problem look like? Well, this is going to be problem number 1. You don't need to draw that. I'll back up for you. Okay, now what I did here is because I want you to be able to look at examples. This is another LH packet, but this is actually the entire chapter 7 in the LH packet, so it's not nearly as bad as it seems. Not as thick as it seems. Well, because I want you to be able to look back at the examples that you need. Okay? So, your homework's going to be on page 419 of this little packet. Now, just like when we were doing area between curves, we'll start with some simple ones where they already give you the region, and then starting tomorrow, we'll have ones where you have to draw the region and set them up and everything. So this is problem number 1. And it's already drawn for you. Normally this problem would look like this. It would be find the volume of the solid formed when you revolve the region bounded by the line y equals negative x plus 1 and the x and y axis when that region is revolved around the x-axis. Notice I put a little arrow here. And I'm going to take this area, again, think of that wedding bell thing from Hobby Lobby that you're going to unfold, right? What shape is this going to make? It's actually going to make a cone because this is an easy little function. It's a straight line. Now, I'm going to draw the other half of it. It's not necessary for you to do this, and sometimes it might even be more confusing for you to do it, but I'm just going to sketch it just so we can see. So if I was to draw the other half of it, if I was to revolve that region around, we can see, hopefully, that this would create a cone. Okay, well, we know this formula for a cone, or we can find it easily, but we'll just check our answer with that later. So notice they put a strip in there, on page 419. They put a strip right there. Now, I want you to think back to this picture right here. Okay? All right? So what we're going to do is we're going to think of slicing this cone. What shape are the slices? Circles, right? And so our formula is the integral will be the area of a slice. Well, our slice is going to be pi r squared, and then the width of the slice. That's going to be our formula, right? There's our area, pi r squared, because they're going to be circular slices. I could even draw one in here if it helps you to see it. Right? There's going to be one slice right there. Now, that strip, remember when we've been working on the strip, so we've been talking top minus bottom and right minus left? That's going to play a big role in these problems. This strip will be a top minus bottom. What part of the slice is that strip? What part of that circular slice is that red strip? It's the radius, right? It's the radius. So here's what I want you to get in the habit of doing. I want you to get in the habit of writing r of x equals, and what would that strip be? Well, it would be the top y value minus the bottom y value. What's the top y value? Negative x plus 1. What's the bottom y value? 0. So that strip is the radius. Before, the strip was the height of our rectangles times the width, and that gave us the area of the region, because it was just height times width. Well, now we're wanting to do pi r squared. So we need the radius of the slices, and the strip is the radius. So we do top minus bottom, we got our radius. All right, so now all that's left for me is to plug it right into my little integral. So I got pi, I got my radius squared, my radius is right there, negative x plus 1. My dx, And then how do you suppose I get the limits on there? The same way they were before. The strips fill the space, or in this case, the slices go from 0 to 1. The strips fill the space from 0 to 1. We go ahead and we type that into our calculator. So all you have to do is set up your integral and then write your answer. I'm going to put a V equals here because this is going to give me volume. What do you get? Pi thirds. Good. And now I'm going to draw something here, but you don't need to. You get the answer pi thirds, and away you go, and don't put units on it or anything else, not a problem. Now, we said that would make a cone. Let me tip that cone up here, and the radius of that cone, the base radius would be down here, that'd be 1. And the formula for a cone is actually 1/3 pi r squared h. That's the formula for a cone. 1/3 pi r squared h. Well, this particular cone has a radius of 1, a height of 1, sure enough, 1/3 pi or pi thirds. And now normally we can't do that because normally the shapes we create are not going to be geometric shapes, okay, like the ones I showed you, the blue plastic pieces, okay? So your homework, we just did the first one. You can do it right in that little packet. You can work it right in that little packet if you want to, because all you really have to do is set up the integral, write down your R. We're going to do 1, 2, 4, 9, and 10. Okay? So just getting this idea, every one of them is going to be a circular slice. Every one of them is going to be this pi r squared formula. The radius will be the strip. They're really fairly easy, but we're going to work over the next couple days of really making sure this makes sense to us as we go along.